course of the past week or so, I've been working on the MIT integration bee, specifically the year of 2015. I'm going to walk through all of the results I have gotten, I'd say, and go through my steps to achieve those results. Some of them may or may not be the same as the results that you see on the MIT integration bee PDF, but they should be algebraically equivalent if I did it right. Now, I believe we can progress to slide number 2, which is simply a reiteration of what I said just now. We can go to the first problem on slide 3. We would like to compute the following integral, which would be the integral of cosine to the 4th power minus sine to the 4th power. Now, this is looking like a tasty difference of squares. We progress to slide 4, and we see that this is equal to a, well, I'd say reverse foiled, or difference of squares. Necessary comment. Cosine squared minus sine squared times cosine squared plus sine squared. We see that cosine squared plus sine squared equals 1 by Pythagoras. So we simply need to compute cosine squared minus sine squared. But we also saw that, let me think. Less saw and more we have memorized that the double angle identity cosine of 2x equals what we have in our integral here.
Actually,
or our integrand.
Tutorial, by the way, right?
Oh yeah, I did! Wow! That is an incredible degree of connectedness.
It's a throwback.
Whoa. Anyways, we see in line 5 that we go through the replacement, and since the derivative of sine is cosine, we go the other way around and find that cosine of 2x is equal to sine of 2x divided by 2. Where, of course, the 2 is because we have a constant inside the function. Yes. Is there any questions on that?
I think that looks good. One small typography comment. Do you see how some of the cosines are italicized and others aren't? So if you type...
Yeah, I see.
Yeah, always put the slash, so slash cosine instead of...
Yeah, I had a lot of slashes missing, and I just kept copy and pasting them, and it didn't go very well.
That's fine. It's a minor comment. The math all looks good. All the steps are correct, and I think it's a nice, as you say, a nice connection that you proved this in the first tutorial. So it's a sense of continuity. But
oh, did I fail to say we go on to slide 4?
Oh, I don't know. I advanced whenever you got here, so it wasn't a problem for me.
Okay. Anyways, we can go on to slide 5, which is question number 2. We want to find the integral of the find me part. What find me? I'm not integral. Anyways, we want to find the integral of 1 over the square root of 2 plus 4x. We are going to go on to slide 6. We're going to do a simple u sub where we have u equals 2 plus 4x, and thus x equals u minus 2 over 4, and du equals 4 dx by the definition of derivative and so on. We make the substitution and see that allow me to remember, due to the combination of the x equals u minus 2 over 4 and the du equals 4 dx, we end up with a total of 4 times 4 times root u on the bottom, and a u minus 2 donated by the x equals u minus 2 over 4.
Wait, sorry, explain the top again. The integral is dx over root 2 plus 4x, right? So where does the u minus 2 upstairs come from?
The u minus 2 upstairs comes from, allow me to remember what the original integral was, actually. Wait, did I make a mistake?
Unless I'm confused, this doesn't look right. I think it should be just...
I don't think there should be u minus 2 up top.
I don't think so either. But is this the right answer that they got in line 10?
I don't believe so.
Okay, let me... Well, I'm just going to pull up their answers really quick and eyeball it. So this is solution 2.
No, mine is pretty different, unfortunately.
Yeah.
Yeah, now I see that I was not supposed to substitute an x up top because there is no x to substitute up top. Ah, Yes, I think I know what I did was someone saying something in JT Talks. Nope.
Wow. I think you saw the
Fair
DX
enough.
upstairs and thought it was an X or something.
Correct. I think it was more. Yeah, that is spot on. Apologies for the incorrect. This was, I think, the first one I did, basically.
That's fine. Can you just walk through, just with words, you don't have to do the details, but what will the solution look like when line 8 on the left just has a 1 upstairs, so it's integral 1 over 16 root u? Then what happens?
I do not believe that would be a 16, and it would instead be a 4. But we would pull out the 4 to get a 1/4 out front and have a 1 over root u. Yeah, just a 1 over root u downstairs, I believe.
Okay, and what's the integral of 1 over root u?
That would be, allow me to think, that is, I have to do it very carefully. It's 2 times root u.
Oh, I'm sorry. What you just said is right. I just looked back at the integration bee. There's a typo on your previous slide. On slide 5, the integral is actually x upstairs. The integral is x over root 2 plus 4x on the integration bee. So I'm sorry.
Okay.
Yeah,
so what I have here is right.
Yes, yeah.
But I successfully handled if we did something else.
Yeah, sorry for grilling you. But yeah, it's with the x upstairs, your line 8 is exactly right. Good. Okay. Go on.
So, assuming that my line 8 was correct, we split the top into u over root u minus 2 over root u, where we pull out the 2 to get what we have in line 9. The integral of root u is going to be u to the 3 over 2 divided by 3, u to the 3 halves divided by 3 halves, or multiplied by 2/3, which gets our first term of the right side of 10. And we also see that the integral of 1 over u, the integral of 1 over root u is going to be 2 times root u. And I believe I should have a -4 instead of a -2 in 10 in front of the root u.
Yeah, the constant on the second term has to be wrong. So, take the derivative of the second term in line 10, so -2 times root u, that's -2u to the 1/2. When you do the power rule, you pull down a 1/2, so that would give you -1 times u to the -1/2 rather than -2, right?
Yeah. Okay.
That's fine. It's just a constant. It's no big deal. Go on.
I believe that is the conclusion of our 2, unless there was any involved definite endpoints.
Well, not quite. Remember, when you're given an integral in terms of x...
Oh my god, did I miss? I missed the substitution back in.
Yeah, you should always plug back in and write it in terms of x.
Man, I butchered this. Wait, no, I didn't butcher this one. I almost did. Anyways, we're going to have that this is equal to 2 times 2 plus 4x to the 3 halves, all over 3, minus 2 root 2 plus 4x.
Okay.
Yeah.
I think that's right. Yeah, up to the factor of 2, I think that matches what they have. They just factored out the root x stuff, so I think it's pretty close. I'm happy that you got the main idea with this one.
Yeah. So we can move on to... Oh, did I miss saying slide 6 again?
No, that's fine. I advanced, but... No, you actually did say slide 6. I remember you saying it.
Okay. Yeah, you immediately push it out of your mind. Anyway, slide 7 for question number 3. Now this is looking like a very tasty u sub, where of course we are going to want u equals root x. We can progress to slide 8 and see that I was exactly right based off what it looked like. We replace u with root x and see that du equals 1/2 root x dx. Pardon me, 1 over 2 root x dx. And the dx is going to eat up the root x in the bottom at the cost of having a 2 du. and the cos of root x is going to be replaced with the cos u, which yields our result in 12. And we mustn't forget about bounds of integration. We see that the square root... did I totally miss? I feel like I'm missing something.
Looks right. No, the bottom endpoint's 0, so you only have that top term, right?
I'm trying to think. I got a 2 instead of a root 8. I know what I was going to... It was supposed to be a 2 root 2, and I missed that. I wonder if it got stuck somewhere. Yeah, you see in 13 that I had a 2 root 2. I just didn't go back far enough to adjust 2 as well.
Wait, what do you mean? The line 13 is
13 endpoint. Compared to 12.
I see. But so you
12's top endpoint should be 2 root 2.
Okay, yeah. So so the final answer is correct, but the intermediate step didn't have the sub done. You say in the endpoint.
Correct. I think it was just me forgetting to do things.
Okay.
And then remembering, and then forgetting to do the entire part of correcting.
That's fine.
This is going great.
You're doing fine.
Anyways, we are going to see that sine of, well, the derivative of sine equals cos, and we can simply multiply that by 2 to get what was in our integral. So we're going to have 2, begin big boys, sine u on the range u to 2 root 2. And of course the 0 is going to contribute nothing to this equation since sine of 0 equals 0. Thus we simply have 2 times sine of 2 root 2. That's a lot of 2's.
Perfect, yeah. That all looks right. It's a cute U sub here.
Yeah. We can now go on to solution 4, which is on slide 9. Now, I was confident, probably because this was the first hard one that I actually tried, that this was the hardest one on the thing. But if we can continue to slide 10, where I literally wrote that out in my final 5 minutes of preparing for this, that we can simply rewrite the secant, the integral of secant is equal to 1 over cos x by the definition of sec. Why am I saying secant? Yes, okay, secant is right, sorry.
Yeah, that's correct.
For whatever reason, I was thinking secant. I'm not dumb. Anyways, we see that we can multiply by 1 in the form of cosine x over cos x to get the integral cosine x over 1 minus sine x.
Sine squared, right?
Now at this point, let's see. Yes, that is through the intermediate step where cosine squared equals 1 minus sine squared x. I was in a big rush right here because this was the last one I did.
That's fine. Okay, so you use...
This is literally, I look down and say 559.
Alright, good. I'll put a sine squared there mentally in my head. Go on.
And I have no idea how to integrate by parts this.
You don't do parts, right? You U sub and then do partial fractions, right?
Oh. Why did I say integrate by parts when I meant partial fractions? Yeah, if we're going to U sub, we are going to let u equal sine x, and thus cos is du. So we're going to have 1 over 1 minus u. Am I correct?
1 over 1 minus u squared, right? Because sine squared.
Yes, 1 minus u squared.
Good.
Let's see. So I believe that would be a 1 plus u times 1 minus u.
Yeah, good.
And we would integrate, we would partial fractions that 1 over 1 minus u, 1 plus u.
Good.
And I am tempted to run through it very quickly. That's going to be...
Yeah, you can just read the steps even if it's not on the slide. Just give us the flavor of how it goes.
We would multiply a plus AU, and we would add to it B minus BU, and we would set that equal to our top, which is simply 1. We would find that. Allow me to think. AU minus BU equals 0, and thus A plus B equals 0. And you would find that A plus B equals 1. So A plus B equals 1 and A minus B equals 0 implies that A equals 1, and thus B equals 1 as well.
Wait, 1 or a half? They add to 1, right?
Oh, yes, sorry. 2A equals 1, and thus A equals 1/2.
Yeah, I think that's right.
Which implies that B equals 1/2 as well. Okay. Apologies.
That's fine.
And at that point, we would factor out the 1/2 from the top of each of these partial fractions and find that this is equal to, let's see, half of log what? Pardon me, negative 1/2 of log 1 minus u plus log of 1 plus u.
Yeah.
And we would substitute back in our u. Wait, where do I have a u? Oh, yes. We would substitute back in our u of, where was it? Yes, sine, to get, I think, log of 1 plus, pardon me, negative 1/2 log of 1 plus minus sine plus 1/2 log of 1 plus sine. There we go.
Yeah, good. Right, so that's actually the answer. You could simplify that with log rules, because log of the difference is log of the quotient, so I think it ends up being like a half log of the fraction 1 plus sine x over 1 minus sine x or something. But yeah, that's totally fine. You can actually prove that the thing you just said is equal to the log of secant x plus tangent x. So that's the way we wrote it before, but they're algebraically equivalent.
Oh boy. That was another fun case. This is the only one where I ran out of time and couldn't write out all of it. Just saying, so that you don't think that 5 through 20 is going to be, oh god, you need to do it all right now.
No.
Apologies.
No need to apologize. That was good. I think you're doing fine.
We can now continue to slide 11, question number 5, which looks very complicated. We're going to be finding the definite integral on the would it be domain or range? Have to check.
Domain, but here we use the word domain in a different way from when we speak about functions, right? In functions, domain is the set of numbers you can plug in, but when we talk about integrals, a domain is just the interval that you are integrating over. So yeah, that's the
okay. Yeah, I used domain somewhere else, and I was checking that it's the right word after the fact. So we are acting on the domain 0 to pi over 2 of e to the sine x over tangent x times cosecant x. We are going to continue to slide 12. So we are going to note the involved trig functions, which would be multiplicative inverse of tan times cosecant, which should be, allow me to remember, cos over sine times 1 over sine? That doesn't sound right.
Cosecant is 1 over sine, but it's in the denominator. So it's cos over sine times sine upstairs, right?
Okay, yes, that is how I got cos.
Yeah.
Apologies, I could not remember, and I did not have time to derive on the spot. Well, not derive, solve. I did it in the work, though.
That's fine.
Alright, so now that we have our integral 0 to pi over 2, e to the sine x cos x, anyways, we see that there is an obvious trig substitution, which is letting u equal sine x, and thus du equals cos x dx. This eats up our cos x in 18, and to replace the sine x with u. And we mustn't forget to change our bounds of integration, which, due to sine of x, sine of 0 equals 0, and sine of pi over 2 equals 1, we get the interval 0, 1 as seen in 19. And we also have that eta sine x equals e to u, cos x of dx equals du, and so on. At this point, we know that the integral and the derivative of e to the x equals e to the x, and thus we can almost automatically go to our big boys. I'm going to keep calling them that. E to the u, where upper is 1 and lower is 0. E to the power of 1 equals e, and e to the power of 0 equals 1. Thus we have e minus 1.
Good. Yeah, that all looks right to me.
Did I ever say slide 12?
That I don't remember, but I advanced.
Oh boy, I always have to ask. Anyways, we can continue to slide 13, or solution 6. Well, question 6. We want to find the integral of x log squared of x on the interval 1 to e. Allow me to think. We can continue to slide 14, where we're going to be applying integration by parts, except in the opposite. Yes. We're going to be applying integration by parts, except in the opposite direction that you'd expect, where instead of moving it onto the x, we're going to be moving the derivative onto the log. So we are letting x equal, if I had a pen, this would be easier. And I do, it just doesn't work because we're not screen sharing. There we go.
Yeah, sorry. If you're going to use the pen next time, we can screen share instead. But anyway, go on.
So we see by integration by parts, we get the result in 23, which is coming from anti-deriving x and taking the derivative of log squared x to get
But that's anti-differentiating. Don't say anti-deriving, anti-differentiating.
Okay, apologies. So we get our subtraction in the left term of the right side of 23. Yep, that's conflated. And we get our different integral again. We're going to apply integration by parts to our right integral. Oh god, I forgot that I wrote that.
Letting log eat the dicks.
Spot on. Alright, we are going to be applying integration by parts, once again moving the derivative onto the log, and seeing that that equals x squared over 2 times log of x for that range, minus the integral x over 2 on the interval 1 to e.
So I know you understand this, but where did the x over 2 come from? What is that product?
Let's see. The x over 2 resulted from x squared over 2 times 1 over x.
Because 1 over x is the derivative of log, right?
Correct.
Good. Nailed it. Okay.
Someone join. Yes, Corbin.
Howdy.
Oh, we have another.
2.
We are on slide 14.
So now that we have our integral x over 2, we can... did I really omit a step here? What I should have done going from 24 to 23, 24 to 25, is we should have found that the integral of x over 2 is equal to x squared over 2 divided by 1 over 2. And thus it would have just been x squared with the big boys.
Wouldn't it be x squared over 4?
Dividing by 1/2.
You don't
Wait,
divide.
no, divide by 2. Sorry.
Yeah.
So, yes, you are correct. It would be x squared over 4 instead of x squared over 2.
Okay.
Got it.
Okay, so that thing in line 25 is the second term on the right side of line 23, right?
Correct.
Okay, good.
So we're going to reinsert this on slide 15. And I believe you can do the arithmetic yourself, but we are going to find that by calculating all the big bracketed boys, BBB, oh god, what have I done? Anyways, we are going to find that the left bracketed boy is e to the power 2 over 4, and the right bracketed boy is probably not going to be 1 over 4 due to an error in my arithmetic.
Yeah, so line 26 is wrong, but line 27 is the answer that the integration bee gave, so you probably just...
I think I got the right answer on my paper as well.
Oh, so you typoed, okay.
Yeah, I copy-pasted 26, well, the right side of 26, so that's what happened. Hi.
I have a question.
Woo!
Okay, so I noticed like before every integral, there's like this line thing.
You mean this
It's like,
curly, the long S thing?
yeah. Is that like to indicate that it's an integral, or?
Correct.
Yeah, it's actually an
That's all I
interesting
wanna
story.
know.
You know how in German, you have that long, the B that looks like an S, that long S thing? You know what I'm talking
Umlaut?
about? No, not the dots.
That's
No, not the umlaut. Etset.
Yeah, is that what it is? Like, I don't know what the rules for that are. I guess when an S is in the middle of a word, you use like the long curly S. Is that right?
I have
It's
no idea.
there. Generally, it's where a double S would go if you were saying it in English.
Okay, that makes sense. But
Well,
yeah.
Latinized.
So the reason the integral sign looks like that, the line that Berno was talking about, is because when people first studied this, they thought of integrals as sums, just adding up a bunch of stuff, right? So you add up, in this case, for those that don't know, it's really adding up the areas of some rectangles. So they thought, okay, we're adding up all of these areas, we're going to call this a sum. But the difference with an integral is it's a sum of infinitely many terms, not just adding up a few things, adding up infinitely many of them. So I imagine what happened is the guys were thinking, well, this is a sum. What letter should we use, or what symbol should we use for a sum that's like really cool and special, like not an ordinary sum? So they're like, well, instead of S, let's use this long curly S, because it looks, I don't know, very elegant or something. So that is why we use the integral symbol that looks like an S, which is stretched out.
I will now refer to this symbol as the big curl.
Good.
Big curly boy is better.
Good.
Or is that what he said and it got cut out?
He got cut out.
Oops.
Nice.
Yes, good question. That Christian could answer, but I couldn't. Lol.
That's fine. It's a fun cultural thing.
No.
So this may be too horribly in-depth, but what is a U-sub?
Let's see. A U-sub is replacing some variable in the integral with something else, and then changing the dx to something else likewise, so that it's the same but in a different format that is easier to solve.
It's a good answer. Pictorially, you could think of it. Think of this as a Python program. If an integral is just adding up a bunch of areas of rectangles, right? You put rectangles under some graph and you add up their areas. You can imagine a Python loop that's like, for I in range number of rectangles, and you just add up a bunch of lengths times widths for the rectangles. So you could imagine changing variables in a certain sense. So in your loop, instead of using like a width w, you could define a new variable, u, which is some different version of w, like u equals 2w, right? So in your loop, you're still adding up all of these rectangles with width w, but now you're going to have to change the rest of the code because you've changed from the width to twice the old width. So you're going to have to compensate and put a factor of a half in somewhere else. So that change of variables, where going from the old widths, say w, to some new variable that you define in your loop, u, which depends on w, that thing is effectively a u substitution. And what Logan's doing here is doing that in kind of the continuous case, not like the Python case, but the continuum case of a function, u of x.
Okay.
Good.
Q. We can now move on to slide 16, which is the integral 1 over x plus 4 root x plus 5. Give me a second to breathe and stretch, because I've been sitting all day.
Inhalation.
And, oh boy, we can go into slide 17, where we are going to be applying a u sub again, where we are going to let u equal root x, and thus we are going to let du equal 1 over root x dx, where of course I accidentally omitted the dx from the du equals dot dot dot. So we see that our base integral is equal to 2u over... Oh, I see. I think I made a... I feel like I made a mistake with the du. Should that be negative 1 over 2 root x?
It should be a half. Du should be 1 over 2 root x positive, right? Because the derivative of x to the 1/2 is 1/2 times x to the minus 1/2, right?
Oh, yes, okay.
But then the factor of 2 is correctly included in your step 29, so it was probably just a typo.
Yeah. So, now that we can now substitute our, let's see. We see that that du equals 1 over root x, and thus dx equals pardon me. We see that since du equals 1 over 2 root x, then du times 2 root x equals dx. So we make that substitution and accidentally forget to apply the, removal of dx and 29 on the right side. Anyways, we replace the root x with our u and get 2u up top. Down bottom we are replacing a x with a u squared, since root x times root x equals x, and thus u squared equals x. We're replacing 4 root x with 4u, and 5 with, pardon me.
And 5 with 5.
Plus 5. Yeah, okay. I don't even know why I even said that.
If your u substitution changed the value of 5, you're in trouble.
Oh god, what system would do that?
I don't know, man.
We are going to, in this step, going from 29 to 30, we're going to be adding 0 in the form of plus 4 minus 4, so that we can split this into 2 integrals. So we are going to have on the left side 2u plus 4 over u squared plus 4u plus 5, and due to how taking derivatives of logs works, we see that the u2 and the 4u are going to donate the 2u plus 4 that we see up top. Now we can consider the right term, where we have negative 4 times some integral 1 over u squared plus 4u plus 5. Now this is similar to a, pardon me while I remember, the arctangent function, but in a different form. So we want to apply completing the square to get something similar. In this case, we are going to have u squared plus 4u plus 4 plus 1 equals u plus 2 squared plus 1. And the integral of 1 over x plus 1 equals arctan x, and thus our right term equals, negative 4 times arctan of u plus 2, or negative 4 arctan of root x plus 2. And we may as well substitute back in the left term on 32, where we let u squared equal x, u equal root x, and so on. Is there any questions? Because this was slightly more complicated, it feels.
No, this is good. I think you explained it clearly. Everything was correct. As a side note, I like using colorful language for describing operations that you're doing. Like when you say that these terms contribute this, or when this term eats that, or something. Most people, I mean, do this when lecturing, like professors and graduate students or something. But it's I'm glad that you start doing it because it makes like the exposition seem a little more fun. So good on you, mate.
It actually makes it easier for me to visualize as well, because, for example, taking the derivative of a log, you don't really think about how the u squared donates something up top until you start using that wording.
Mm-hmm. Yeah, it makes it very, very visual, and you can kind of feel the terms that are going to come out, like in your gut. I like it.
Oh boy. Did I ever say that we were going on to slide 17? I don't know. Yes, I did. Okay. I'll just stop asking. We can go on to slide 18 now, which is, yes, a reminder of the math competition obsession involving the current year. We want to find the area under the curve of 2015 to the power of x. So we are going to recall that e to the log x equals x. Continue to 19. So we are going to apply. Huh?
In that sentence, it should say
e to the log.
Okay, that's e to the log z. It should be right.
Yeah. Oof. I see what's going on here. e to the.
By the way,
I'm sorry. I'm laughing at that.
In LaTeX, if you're ever typesetting something with a superscript that's more than one character, you have to put it in curly braces. I think that's what happened.
Yep, I noticed that.
Okay, good.
I did it fine for all the other ones except for that. Anyways, we see that since we place e to the log of 2015 x, we can pull down the x because e to what power, we can just pull the x through and out. And then we see by derivative taking intuition that we're going to have to divide out the log 2015. And since e to the x is its own integral and its own derivative, we are going to paste it back into 35. And we still have the x and log 2015. So we reinsert the x into the log of 2015 and simplify it back down again to 2015x over log 2015. Does that explain clearly?
Yeah, I'm happy with that. So I know I've hammered this a bunch of times, but can you just remind me, why can't I just use the power rule and say, integral of 2015 to the x, whatever?
Inhale, because x is a variable and not a constant.
Good, yeah, so in the proof of the power rule, we explicitly assumed that the base was a constant, and the base was a variable, and the exponent was a constant. Good.
Inhale. We can now move on to slide 20, which is the mildly complicated integral, definite integral, may I add, on the range 0, 2, well, interval 0, 2. Anyways, x over x minus 3 times x plus 5 squared. We're going to be applying, we can go on to slide 21 and see that we're going to be applying partial fractions. Now, I'm not going to walk through the algebra for this because it's just not worth doing. But take it as given that we're going to have that our first term is going to be 3/64, second term negative 3/64, and third 5/8. This is going to be breaking it into much simpler integrals to deal with. Someone was calling me. I don't recognize the number, so I'm just going to have them leave a voicemail. I don't care.
Good.
We are going to be pulling a 3/64 out of the first two integrals and forgetting to add it, well, multiply it back in 39, 40, and 41, sorry. But we are going to see that, wait, why did I multiply them?
Yeah, I think that should be added, right?
Yeah. Oof. Actually, they should be subtracted.
Oh, yeah, because the minus 3/64. Good, good.
So we factor out a 3/64 from the first two terms, and we see that the third term can be handled with the power rule, where the power rule is going to pull off the to the power of 2 in the denominator and multiply by -1, so that a plus 5/8 equals, well, becomes a -5/8.
Good.
Had to adjust my wording very quickly. Now, we also see that 1 over x minus 3, well, the integral 1 over x minus 3 equals log of x minus 3. Similarly, the integral 1 over x plus 5 equals log of x plus 5. So we have our left two guys and the big boys. But of course, there should be a subtraction sign in there due to the negative 3/64 when I factored out a 3/64.
Good.
So we're going to calculate at those values where we note that, let's see, I feel like there's things missing.
You forgot the top term, so you plugged in the 0.
Yeah.
But you should have a log 7 and a log... oh, you also forgot the absolute values. So remember, when you integrate 1 over x, I usually just write it as log x, but if the argument becomes negative, if x becomes negative, technically you should write that the antiderivative is log absolute value of x. And that actually matters here, right? Because 2 minus 3 is a -1. So you'll need the absolute values to get the right answer.
Oops. Okay. So a quick note on absolute values and that I missed the upper term. But we see that the right term I am pretty sure I did right. And the thing inside the big boys becomes a -5/8 times 1 over 7 minus 1 over 5.
Good.
Just by plugging in the values and subtracting the 2.
Yeah, that looks right to me. Good, good. So basically all of the calculus is correct. It's just maybe the algebra stuff at the end might have a small error, but that's fine. I'm happy with this.
There's a lot of little problems. At least it feels like it.
That's fine.
I didn't have time to read over it. Oops.
You're too hard on
22.
yourself. I mean, the important part is being able to do the integrals, and I think you've nailed all of them. So, I mean...
So we have question 10, which is on slide 22. We're going to, just by observing, I believe we are going to let 1 plus log x equal u, and going from there, we can move on to slide 23, where that is exactly what I do. We see that letting by letting log of log x plus 1 become log u, and letting the dx letting the dx if I could stop saying equal and instead say eat, that'd be great. If we can also let the dx eat the 1 over x present in the base, and see that what we have to start is equal to the integral of log u. I'm doing too much talking, not enough writing in this slide. We see that by basic log rules that this integral is going to become u times log u minus u.
By basic log rules, you mean, integration by parts, or just...
Yes, not basic log rules, but yeah, integration of a log equals variable times log variable minus variable. Yeah.
Yeah, good. You proved that in a previous slide, so that's fine. Yeah.
Okay. Now we see that by reinserting what u equals, we're going to have log of x plus 1 plus jazz in 44. I'm reasonably sure this could be simplified.
Yeah, but...
What does the paper have? We are on 10? Actually, I think this is exactly what they... Did I lose a negative somewhere?
Yeah, I was going to say, they have a relative minus sign, and they have, something weird.
Log x times... wait. don't know. We'd have to graph it to figure out if it's the same or not.
You don't have to graph it. You can use mathematics.
True.
But, yeah, up to this minus sign, I'm a little confused about, but otherwise it seems reasonable. Why is
As far as I can tell, all the steps are correct.
Yeah, certainly up to 43, and then 44 is just plugging back in. So, yeah, I mean, we could check the algebra later in Mathematica, but I think your reasoning all seems pretty good. At worst, there might be a small sign error or something.
Yeah.
Okay.
All right. So that one is concluded
Halfway
very
through,
quickly.
questions or comments from the audience.
Oh god, it's been 50 minutes and it doesn't feel like anything.
You're in flow.
Bina and Corb, question mark.
Bina's muted.
Any questions?
I don't understand what's going on, so I can't really form a question.
Darn.
It looks neat, though, and it sounds neat.
Okay. Neat is good.
It kind of makes me want to smash my head against Calc more.
Oh boy.
It's motivation.
Actually, I think that's the purpose of
Motivation
your
for suckers.
I think.
The purpose of what?
I think the seeing what is ahead was the motivation behind your what's the proper name? Look ahead sections of certain sessions.
Oh, the previews, I called them. Yeah.
Yes.
Yeah. Oh, can I ask a real quick question? I want to do a preview deriving the ideal gas law. Have you seen that in chem yet?
PV equals nRT?
Yeah, that.
Okay, sure.
Okay. It's a little tricky. You have to know the integral of e to the minus x squared, which you remember is root pi when you go from minus infinity to infinity. It's actually the only integral you need
Wait,
to
the definite or indefinite
definite
of that?
definite from minus infinity.
Because the indefinite doesn't exist, right?
The indefinite, you just give it a new name. It doesn't exist in terms of other functions, so you just call it, this is the error function. Yeah. But,
Lovely.
Okay, good. So
Wait, what does that have anything to do with the ideal gas law?
you needed to prove the ideal gas law, right? In chemistry, you just write it down and say this is true. In physics or in statistical physics, you derive it, and you need that integral to do it.
Is there any math course? Is there any statistical chemistry courses, or is that?
Yeah, no, you do the same thing in physical chemistry, they call it. Or if you take thermodynamics in chemistry. Thermodynamics and statistical mechanics are closely related. So if you take a physical chemistry class or a thermo class from the chem department, you may also see this proof of the ideal gas law. But I mean, if you needed more motivation for why we need to do all of these hard integrals that seem to have no applications,
They're fun.
Well, they're fun, and I will claim to you that you cannot even understand why the ideal gas law is true unless you know that the integral from minus infinity to infinity of e to the minus x squared is square root of pi. You need it.
There's a lot of things you can't understand. Is that right?
Oh yeah. I mean,
You don't understand that?
yeah, if you don't understand, that's why that one was written on the wall in the MIT tunnels. You remember, right? Because it's
Yeah.
that is the most important integral in probability and statistics because it's the area under the bell curve, right? Good. But that is an aside. I'm interrupting you.
But it's an interesting aside. We're halfway through page-wise as well.
How nice.
Yeah, that's what you said. It is 6:53. I'm doing okay. We can go on to slide 24. This one.
Yeah.
We're going to be finding the area under the curve of square root of cosecant minus. It is so random now that I think about it.
It's cooked up.
Yeah, we can move on to slide 25 to see that we're going to be multiplying this integral by 1 in the form of root sine x over root sine x. We see that the sine x in the square root passes straight through to the inside of the square root of our integral. Cosecant times sine x equals 1. Sine x times sine x equals 1. Well, pardon. No, that is false. Sine x times sine x equals sine squared x.
Good.
Audible annoyance from Christian.
not annoyance. I was just like,
Anyways, we see that there's also a donated, I'd say, denominator of root sine x. Thus we have the end of 46 square root of 1 minus sine squared x over root of sine x. Once again with the formatting errors, but we can also notice that the square root of 1 minus sine squared x equals cos x. So we are going to have our result in 47, which is cos x over root sine x. We are now going to apply u sub where we let u equal sine x and thus du equals cos x. The dx eats up the cos x and makes it a du, and the sine x in the bottom becomes u. And we simply apply a power rule where we bring it up a power and divide it by 1/2 or multiply by 2. And then we reinsert u equals sine x to get 2 times the square root of sine x. Clap.
Kind of a cute result for an integral that at the beginning looked like it was out of left field, this weird square root of a difference, but it comes out to be pretty clean, right?
I mean, the input was pretty clean, it just didn't seem to make much sense.
Yeah, that's true. It looks pretty uninterpretable, I agree.
We can... Wait, did I say slide 25? Yeah, I probably did. We can move on to slide 26 now. So we're going to have the integral 1 over square root of x squared plus 25. Now, I cannot remember how I did this, so we're going to go on to slide 27, and I'll remember from there. Ah, yes! Tasty. Pardon me a second. So we are going to be performing a trig substitution, since we know that the square root of something squared plus 1 is some other, allows us to simplify to some other function. Anyways, we want to let x equal 5 tan of theta, which implies that theta equals arctan of x over 5. And dx equals 5 times secant squared of x over 5. Is that right? I feel like something isn't quite right with the transition between my x equals 5 tan theta and my dx equals 5 secant squared x over 5.
That's right. Just look at the left, the far left of line 50. The x is 5 tan theta. Hit both sides with a d. On the left side, it's a dx. On the right side, it's 5 times the derivative of tangent. Oh, yeah, which is secant squared. Okay. Okay, but then you put in, oh, is that right?
Divided by 5. Yeah, it's not.
No, that's, okay, good. So there's, yeah, that should be dx is 5 secant squared theta d theta, right?
Correct. Woo! At least catching these errors instead of just going right past them and not noticing.
Yeah, that's good. It's not a bad thing. I mean, if there are errors, that gives us additional opportunities to think when we're looking at them, which is what we're doing. So this is good.
We see that by replacing our dx with our 5 secant squared of theta, we get that the top of the integral equals 5 secant squared theta. And by replacing x equals 5 tan theta, we're going to get that we can factor out a 25 out of what was originally 25 tangent squared plus 25. And we pass this 25 through the square root to become a 5, and it divides with the 5 in the top to equal 1. We know that tangent squared plus 1 equals secant squared, but we have this square root, which makes the denominator become secant. And we see that the top is going to become, after the 5 is divided out, secant squared.
Good.
So we are simply going to have the integral secant of theta. We can move on to slide 28 and refer back to our solution and, well, the given solution for number 4, but not my solution for number 4. And see that we're going to get that secant of theta equals what's the proper word? The hyperbolic arcsecant?
Yeah, hyperbolic arcsecant or sech inverse or whatever. People pronounce that sech sometimes.
Yeah, it's a lot easier. Sure, sech of cos of arctan of x divided by 5. Once again, referring back to our definition of theta equals arctan of x5.
Yeah, so that's not the form that you wrote the integral of secant in, right? Because you had this log of 1 plus sign and 1 minus sign or something?
Yeah.
But
At this point, I did not have 4 completed and decided to steal the splash. I think 4 and 5 gave me the biggest problems. I think I had ideas for them down, said I was done, and fixed them today.
okay, that's fine, because this thing in 54 is algebraically equivalent to your answer, and you could actually simplify it and write it as a log, but whatever, we don't need to simplify. I'm happy with this.
Now I can go on to slide 29, since that actually didn't have many errors outside of that dx equals jazz. Slide 29, the definite integral on the interval 2 to e of log squared x minus 1 over x log squared of x.
Before you begin a thing, I must disappear, and I'd like to say that this looks cool, and you did good work. Yee.
Cool.
Oops.
Ciao, Corbin.
See ya.
Yes, food has arrived. Adios.
Bye. Food.
Just read Verna's comments on Discord. I like how Lug sounds and says words.
I agree, actually. Your exposition, you're getting better at speaking more comfortably and in your own voice, which I think you improved a lot even just before Splash, but I don't know, it feels, more conversational the way that you're presenting this. So I agree. I like the way you say words.
Whoops. So we see immediately that a likely u substitution that can occur here is a u equal log x, and we move on to slide 30 to see that's exactly what we do. It's almost as if I did these. First, we're going to find that, pardon me while I think, we're going to find that the bounds of integration change due to u sub, where the lower bound is now log of 2, and the upper bound is now e. Of course, we're assuming log is the natural log. Inhale.
Like civilized people.
Yeah. We see that the u equals log x, and thus the top is u squared minus 1, and the du equals 1 over x dx. That is going to eat up the x in the bottom, so that the bottom simply becomes log squared x equals u squared. We can now split this into 2, where the left side is u2 over u2, and the right side is minus 1 over u2. Was that a snicker?
I'm snickering at saying U2 instead of U squared, but maybe you want to...
Oh boy! Shh.
Hushing.
That's just how it ended up. I started saying it and I couldn't stop.
I assumed you were doing it kind of as a joke, because it was kind of funny. It sounds like the band U2.
It wasn't a joke, it just happened.
Whoops.
So we have the integral log squared to 1. Why did I say log squared? Oh god, I'm doing it the wrong way around now.
All 2's are squares.
All squares are 2's. Done. Anyways, we have the definite integral on the range log 2 to 1 of 1, which is equal to the big bracketed boy of u on 1 to log 2. Meanwhile, the right side is by the power rule going to gain a minus sign, which turns the right side positive as a whole. And the u squared becomes a simple u. Once again, we have a big bracketed boy, and it is acting on the range 1 log 2. Well, not range, not interval, points. There we go. We see by evaluating this at those points, we're going to get 2 minus log 2 plus 1 over log 2.
Okay, good. This looks right.
Is there any questions from the 2 people watching?
Well, one of them left. I don't know if Berna has questions because she muted, right?
Technically, you're watching with Chris. Lol.
Did you just call me Chris?
Yeah,
Nice.
deal with it.
Yeah, this one's pretty cute. It's similar to
Yeah.
which one? There was the log one before in question 10 that had a similar substitution. So, yeah, this one's pretty nice.
Oh yeah, that was similar.
Yeah, I like the way you described it as the dx eating the 1 over x, because it trains your eyes to see when you look at the integrand on, say, the left side of 56, and you see the dx and the x downstairs. Eventually, if you haven't already, you'll just see that, and then like your eyes will see those and say, oh, u equals log x must be the right thing, because then the dx will eat that 1 over x, and I'll have something pretty, right? I suspect you're already thinking that way based on the verbiage you're using, the words you're using.
Yeah.
Good.
We can go on to slide 31, which is question 14. The integral of e to the 3x times arctan ex. Sniff, snort, etc. We see that e to the x occurs twice here, quote unquote. Why was I physically quoting if no one can see me? We can go on to slide 32 to see that we applied the u sub u equal ex, and thus du equals ex, to see that our dx is going to eat up one of the powers of u on the left side, and there are going to be ex times ex remaining, or u squared. Meanwhile, the ex in arctan is replaced with a u as expected. Once again, we are going to be moving integration by parts onto the opposite of what you'd expect, where in this case we're going to be moving the derivative from the u squared onto the arctan to get u to the third over 3 arctan of u minus a factored out 1/3 of the integral u to the third over u squared plus 1, where u squared plus 1 is the derivative, 1 over u squared plus 1 is the derivative of arctan.
Good.
We can then apply the polynomial long division to the right side of 62 and see that u to the third over u squared plus 1 equals u plus u minus u over u squared plus 1.
Good.
We can go on to slide 33 to see that these two terms are going to be equal to u squared over 2 in the case of the integral u, and the right term is going to be equal to half of the log of u squared plus 1, where we are halving out the u that remains after taking a log to get what we have in the top.
Yeah, the half because you get the 2u down from the power rule of the inside guy, right?
Yes.
Good. I like how you call that an intuitive log. You are also
Oops.
an intuitive log.
Oof. Wait, intuitive does not have any correlation with chaos.
I don't think so, unless, well, maybe you think you are chaotic, but that's not what I was getting at.
What? Now we can reinsert our right side back into the integral we had in the equation on slide 32 or equation 62? Yes. So we're going to have u to the third jazz, where we have reinserted the integral with its given values. I don't see any need to simplify things. Huh?
In line 65, the u cubed, you probably should have put that as an e to the 3x, right?
Oh yeah, that'd help.
Yeah. It's just everything else is subbed back in. It's just that last one you didn't do, but that's fine.
Yeah, I missed it. Whoops.
Yeah. Good.
We can now move on to slide... do you have any questions or comments or concerns, or thoughts, comments, questions, concerns, death threats?
No, certainly not death threats, no. I was just saying good. I apologize for interrupting.
I had to check. Question 15 or slide 34. Absolute values are fun.
Yeah.
Quote unquote.
Who are you quoting?
Myself. Scarecrows, I think I was going for.
Log scared.
But anyways, I forgot their bounds of integration.
What were they?
It should be the definite integral in the interval 0, 4, rather than what we have here.
Okay.
Allow me to think. Alright, we're going to be breaking the integral into 4 different parts that are in line with where the absolute values turn positive or negative and match their inputs or whatever. Continue to slide 35 to get a better idea of what I meant. We're going to see where we confidently replace the absolute values with parentheses and some plus or minus so that it equals what you would get normally. Because we don't normally know how to, well, I personally do not know how to handle absolute values and integrals outside of this.
So this is all I know how to do too.
Whoa. Wait, that's an entire how many extra years of math experience, and it's the same idea.
I mean, yeah. You don't, when you go on in mathematics, you don't spend a lot of time thinking about integrals of absolute values. So this is the end of the line as far as that line of inquiry goes.
That can be fixed. Imagine there is just someone dedicated to absolute values and integrals.
Full time. This just grinds them out all day.
Is that who they hire for literally any AP Calc BC course?
Oh God, such a grind. But good. Okay, so in line 67, all of those guys are negative, so you put minuses in front of all of them. Is that right?
That is correct. In the case of line 68, everything in the bottom was negative, but the top could be left the same because 1 to 2 does not include the point, well, does not have any negative values when it comes to the absolute value of x minus 1.
Good, nice catch. Yeah, you almost said it was all positive, but then you switched to basically saying non-negative. Good.
Oh, you noticed that?
Yeah, you were going to say it's all positive, then you realized that when at the end point 1, it's not positive, it's 0, and then you just said it's not negative, which is good. That your precision is spot on.
Whoops.
Why whoops? I'm praising you.
I don't know. Keep hearing myself and it's totally pleasant. Let's see. In the case of 69, we're going to be seeing that the x minus 1 and the x minus 2 are going to be non-negative, and therefore they can be left as b, but the x minus 3 must be multiplied by negative 1 to represent what the absolute value does. This means that we just get x minus 1 over 5. In the case of 70/71, for whatever reason,
I think you put
we get that all of these are going to be positive, and thus we don't need to do any negatives, and we can simplify as we see it.
Good.
We can go into slide 36. The first two are going to sum to 0, since they have the same denominator and opposite signs for all of those. If you want to go back to 67 to 68, so just to check. Don't know if I should save that or not.
Yeah, I see it. I went back. Good.
We can continue back forwards to 36 and sum up the two remaining, which were, allow me to think, 70 and 71, or, pardon me, 69 and 70/71. Yeah. So we can get a common denominator by multiplying each
Whoa.
by the...
Why? Why are you combining them?
I don't know. I don't know why I'm doing that.
Yeah, if you go back to...
That's a good question.
Go back to slide 35 and look at 69. So why combine them into a single integral when you could just do them separately? Like line 69, yeah, it's just x squared over 10 minus x over 5. 70...
Yeah, I don't know. 70 is the only one I might need to do some furkery for.
Yeah, but you just have to add 0 up top. You add it and it's like x minus 4 minus quantity x minus 4 or something. But anyway. So. Oh, you even said add 0 in a peculiar way. Thanks.
Yeah, I hinted at that. That's probably a better way to handle it, but I just realized I'm very loud.
No, you're not. You're so self-conscious.
Oops.
Log whoops. But okay, yeah. So line 74 is correct, but it just made it more complicated, right? So
Yeah.
yeah.
So I could do polynomial long division. It's not the most efficient, but it is technically equivalent.
Yeah.
I didn't do the polynomial long division.
Log whoops.
So I was lying when I said there was no other ones that I missed on 6 or 5 or 4. I can't remember.
Well, that's fine. I think the key insight to take away here is that in absolute values, you usually have to break it up into intervals where they have constant signs. So I think you understand that because you explained the breaking into 4 pieces very lucidly, I thought. So yeah, this is probably good enough.
Yeah. We can go on to 37 or question 16, which is the definite integral on 0 to 2 pi of 1 over sine to the 4 plus cos to the 4. Now, before you go any further, I'll say that I didn't do what the hint suggested the first time around, and I did sine squared plus cos squared times sine squared minus cos squared in the denominator, but that didn't work very well. Huh?
It's not true that sine to the 4th plus cos.
Oh my god!
Difference of squares, not sum of squares. Did you just throw your headset or something?
I threw my headset back out of just, oh god, how did I mess that algebra?
Called it.
Well, what did you call?
When after you threw it, I said, "Did you throw your headset?" And then you came back and said, "I threw my headset."
I didn't actually throw my headset. I just leaned back far enough that it fell off my head.
Lol.
And quickly.
But yeah.
As I was trying to say, yeah, I see that doesn't work now because it's not sine to the 4 minus cos to the 4.
But notice you can fix that. I mean, difference of squares is nice because x squared minus a squared is x plus a times x minus a. If you ever really want to do sum of squares, you only have 2 options. You either, 1, make one of them imaginary, right? Because x squared plus a squared is x plus ia, x minus ia, because then those 2 i's give you the plus. Or you convert your sum of squares into a difference of squares and then subtract the cross term. And that's what you do in the hint. So make note of that.
Yeah.
That comes up in math competitions all the time, where there's a sum of squares. Sorry.
That's what I did in 38, I believe.
Yeah, good. Sorry, I'm stealing your thunder by saying this.
Did what is quote-unquote completing the square. And the left term is going to be sine squared plus cos squared, quantity squared, but that is just equal to 1, as we see in 76. Meanwhile, we subtract away the term that would appear, which is 2 sine squared x times cos squared x. As I worded it, we have praised Pythagoras to handle the left squared term, and we are going to recall that sine... Why did I write down sine double angle formula instead of just writing down sine 2x equals jazz? Well, 2 sine x times cos x, yeah.
No big deal.
So we are going to replace 2 sine squared x times cos squared x via the sine double angle formula to see that we have the still definite integral 1 over 1 minus a half sine squared 2x. We can go on to 39. Oh!
Whoops.
That's not good.
Oh no. Did you run out of time or something?
I guess so. I don't even remember this one.
Whoopsie. Did you solve it on paper? Do you know what to do next?
I think my solution on paper was wrong. I got like a 0 minus 0.
Ah, okay.
Why does this keep happening?
Oh, that's fine. I mean, the next step, after you get that sine squared stuff in the bottom, I think is to do some... yeah, you can manipulate that. It's a little tricky, but I think you manipulate that by multiplying top and bottom by some cosines or something to turn it into an expression involving secants and tangents.
Yes, I remember that. Secant over 1 plus tan or whatever.
Yeah, I think it's like secant squared over 2 plus tan squared or something. And then you do a u sub. because then it looks basically like arctan. So it's actually kind of cute. It looks like the answer for the indefinite integral ends up looking like an arctan of a tan of something with a coefficient or something, which is, I don't know, it's pretty, but
Okay.
yeah, all right. Yeah, it might be good just for your own benefit to, if you either work it out on paper and convince yourself that the answer that they wrote down is right, or add it in the slides or something, because I think these slides should go on GitHub. But I don't know, just it's a fun integral. I like this one, so it's worth
Are you
writing.
keeping track of the errors?
I am not. I apologize. I can.
I was just curious. I'll read through this again when I'm less stressed.
Why are you stressed now?
I'm not stressed.
Oh, okay. A strange sentence then.
I was stressed at 5:55.
Oh, okay. So now
It was a very good feeling stress for whatever reason.
seems like it was a productive stress, but you feel good now. You're happy presenting, right?
Yeah, I've been happy
Glad to hear it.
since like 10 o'clock.
Ah, good.
Anyways, we can skip over slide 39 and head to 40 to the next completed integral, which would be 1 plus x over 1 minus ex. I mean, 1 plus x, good job. 1 plus e to the x over 1 minus e to the x.
Good.
We can go into slide 41, where we break the integral into two pieces, 1 over 1 minus e to the x, plus e to the x over 1 minus e to the x. Let's see. Now, what did I do? Oh, I reordered it. That's why it looks strange.
What, from 79 to 80, you mean?
Yeah.
Yeah.
Anyways, we see that 1 over lag. Lots of it.
Oh, sorry. I was just agreeing with you. Sorry. Go on.
Okay. So we see that the integral of 1 over 1 minus e to the x is moved down to the right of 80, and the integral e to the x over 1 minus e to the x is equal to the negative log of 1 minus e to the x, based off of how the log passes things through to the top as well, if they do not vanish.
Chain rule, right? Derivative of the inside, right? You mean?
Yes.
Good.
Just a different way of wording the chain rule, I guess.
No, I agree. Sorry, I wasn't correcting you. I like the way that you said it better. Actually, I was just commenting to say words. Sorry.
Yes.
Passing through to the inside is a nice way of phrasing it.
Okay. So now we have to handle the integral 1 over 1 minus e to the x. So we see that we can let u equal e to the x, and thus du equals e to the x dx. And thus dx equals du over ex. So we replace our integral 1 over 1 minus e to the x with 1 over 1 minus u times 1 over u, which we got from that dx equals du over ex. So now we are going to apply the partial fractions in slide 42. And we see that both a and b are equal to 1, and thus our left integral is equal to the integral 1 over u plus 1 over 1 minus u. We see that the left integral is log of u, or log of e to the x, and thus is simply x. Yeah. And the right integral is a log of 1 minus u, but we have to multiply that by -1 to handle the negative u. So we simply have x minus log of 1 minus u, or log of 1 minus e to the x.
Wait, is there... Their answer has a factor of 2. I think we lost a factor of 2 somewhere. They have x minus 2 log 1 minus e to the x, which I think came from... where did this... Is this right? I'm confused now. You see where we lost a factor of 2 somewhere?
do not see any place.
Integrate logs. Yeah, I'm confused now. Where did this come from? So
Where did it come from?
all these steps look right. So 1 plus e to the x over 1 minus e. Okay, I'm just going through again. So log 1 this, 1 over u times 1 minus u. Okay, I'm totally confused about why they... Your steps look completely correct. So why do they say there should be a factor of 2 in front of the log, the second piece? Minus e to the x. No, Mathematica agrees. There's supposed to be a factor of 2. So, okay, we did... I don't know if it's that important. Somewhere there's a factor of 2 that's supposed to be here from... Oh, I see. Duh. Sorry, I'm being silly. Line, excuse me, line 82 and line 83, you are evaluating the second term in your equation 80, right? Equation 80 is a sum of 2 terms, and you're only evaluating the second term. So you have to add that back to the first one. There we go. Man.
So, yeah. Got it.
So
Negative. It would be 2 negative log of 1 minus e to the x jazz.
Yeah.
Okay. Whoops.
Sorry, I apologize for wasting time on that. That was a silly mistake. I just wanted to...
No, it was a mistake we needed to find.
All right.
I concluded too early. I finished too early.
Ooh.
But we can go into slide 43. The integral of tangent to the 4th power of x. This was actually quite fun. I think this was the first hard one I did well.
Nice.
Now we can go into slide 44, where we remember that secant squared of x equals tangent squared of x plus 1. We're going to substitute one of our pairs of tangents for a secant squared x minus 1 in the original integral, and see that this is equal to the integral tangent squared secant squared dx minus the integral tangent squared dx. We're going to apply a u sub to our left term on the right side of 85, where we let u equal tan x and du equal sex. That was bound to happen. Secant squared.
Please tell me that was intentional.
No, it was not. Secant squared of x dx. The dx is going to eat up the secant squared, and the tangent squared becomes a u squared, as we see in the left term of 86. The right term is going to get split again, where we let tangent squared equals secant squared x minus 1. So we have the integrals on the right side of 86 in the parentheses as a result of the right term of 85. And we simply evaluate each of these, where we apply the power rule to 1. We remember that tangent, the derivative of tangent, is secant squared of x. And you heard that.
Yeah, why did you smirk on secant squared? Were you about to say sex again?
Because now it's actually harder to not say it again. Okay, anyways, the integral of 1 is going to be just x, and there's 2 negatives, so it becomes a positive x.
Good, but don't you want to sub u back in when you write this to get an expression in terms of x?
Yes, that's a good idea. U equals tangent x, and thus tan 3x. Tangent to the power of 3 over x. No, tangent to the power of 3 of x over 3 minus tan x plus x. Clap, clap. I did it.
Good, yes, that is correct.
You know that? I don't know. Never mind. I was going to say, for whatever reason, I'm reminded of the log u du formula, but it's actually nothing similar.
Log u du. You mean integration by parts to get the x log x minus x thing?
Yeah, for the, I don't know. It's totally different than what we got in 87. So I don't know why I was starting to say that. It almost looked similar.
Yeah, you still have them. It's almost like the minus x piece. I think I see what you're saying. But good.
We can go on to slide 45, which is the integral sine of x times tangent squared x. We can go into slide 46. Once again, we're going to remember that tangent squared of x equals secant squared of x minus 1.
Are you going to smile every time you say secant now?
Stop! We see by basic multiplication that we're going to get that sine x times secant squared of x equals tan x over cos x. Meanwhile, sine of x times -1 equals negative sine of x. Getting our two terms in the right side of 89. Our right side is going to become a cos of x, as we see in, pardon me, it's going to become a negative cos of x, but the terms cancel to get our cos of x in 91. And now we want to consider the left term, the integral of tangent over cos x. We're going to u sub, where u equals secant x?
Wait, what's going on here? So you're integrating.
Oh, I see. We are letting u handle the cosine in the bottom. What?
But you want du to kill the cosine at the bottom, right?
Yeah, something doesn't quite right here.
Maybe what
Was
you...
this actually u sub?
Yeah, yes.
No.
You could do it like...
What?
So another way to do it is to say tangent to sine over cosine. So line 90 is the same as sine x over cosine squared of x. And then you would let u be cosine. So you'd have a u squared downstairs, and a du gives you the sign that kills the sign upstairs. But I think what you're doing there might be equivalent after some algebra. Because just instead of u equals cosine, you're doing u equals 1 over cosine, right?
Yeah, I don't remember how I got that. That's weird.
Oh, I see. Sorry, I'm being dumb. Tangent over cosine. 1 over cosine is secant. So you can write the left side. You can write tangent over cosine as secant times tangent. So,
Oh, that's what I was doing.
actually, that's clever. Actually, I like your way better, actually, because then the secant tangent just all gets eaten, right? And then you just get du. Okay, your way's
Oh,
better.
that is cool. I forgot how cool that was.
Yeah, that's very pretty, actually.
So our integral simply becomes 1 du, and we see that that becomes u, and u equals secant of x. So we see in the bottom that our left term on the right side of 91 is secant x.
Good.
Thus we have a result.
That's cute. I like that result. The result is cosine plus 1 over cosine, right? Because secant is 1 over cosine. I like that.
Yeah. We can go on to see that. Why am I saying go on? We can go on to slide 47 and conclude with a fairly simple integral. We have the integral of x plus 1 over x squared plus 2x plus 3, and go on to slide 48. This is something I could have just done with a guess and check log. Well, not even a guess and check, just have the log. But instead I decided to just make it clear and use u sub, where we let u equal x squared plus 2x plus 3, and thus du over 2, what I was going for, equals x plus 2.
X plus 1, right?
Yeah, x plus 1. So we pull out a 1/2, and this is going to become 1 over u, or a half of log u. We reinsert u to get a half of log of x squared plus 2x plus 3.
Nice. Very good.
Oh boy, that was all slides. I did not have a conclusion.
No, it's fine. You were just solving a bunch of problems. Okay.
Yeah.
Good. Let me stop the recording.